Hello, so we are going to start with our first review of properties of water and just basic chemistry of life. Hopefully this will help. Please watch this video as many times as you need to stop it. This is a PowerPoint that is in Blackboard, and it will be the same for every single PowerPoint. Everything is on Blackboard for you to look at it any way you want to. So we are going to start with a basic review of chemistry and properties of water that apply basically to biology, what we are going to be doing all day long. As you know, everything is made out of atoms, and this year we are going to be talking about a few atoms over and over again. Please remember that all atoms are made out of protons, neutrons, and electrons. Protons and neutrons are located in the nucleus. Protons positive charge, neutrons no charge, and the electrons fly around. So the smallest one, of course, you know, is the hydrogen atom that only has one proton in the nucleus and one electron flying around. Down here we have the oxygen atom that we are going to talk a lot about oxygen through the year. Has 8 protons in the nucleus, 8 positive charges, very important, has 8 neutrons, no big deal, but it has 8 electrons flying around. Oxygen, I need you to remember, oxygen is one of the most electronegative elements that we have in biology, electronegative, and if you want to remember it in a simple way, just call it an electron sucker. It's the biggest electron sucker. Because, in simple terms, it has 8 positive charges here that are pulling every single electron that they can come across towards the center. So please remember that. Oxygen in biology is what we call an electron sucker. It's very electronegative, and that's going to be important for everything pretty much that we study this year. In life, in biology, we're going to deal mostly with a few elements over and over again, and we're going to talk about this all year long. That's why it's so important that you get it from the very beginning. Carbon, hydrogen, oxygen, nitrogen, CHON. If you remember CHON from your freshman year, CHON, this is a little bit too thin, and let's make it more colorful. CHON. Carbon, hydrogen, oxygen, nitrogen is what makes most of your body, most of the molecules. And then we have a few other things that are going to be adding around. Phosphorus, if you're talking about DNA. Sulfur, if you're talking about proteins. Calcium, potassium, sodium, a number of other things that we have in smaller amounts but that are critical for the functioning of our bodies. So just a little heads up of what's coming. An important concept is isotopes. I know you've studied this, and basically these are different forms of the same element. Carbon is carbon, has whatever number of protons and electrons, no problem. What changes in isotopes is the number of neutrons. So protons and electrons is what gives an element its properties, but the neutrons is what makes different isotopes. And that's going to be very important. So for example, if you have isotopes, the extra number of neutrons, you know, sometimes they break down, they give off particles, energy, and that's going to be important in biology because we can use them as tools to figure out things. So for example, you are all familiar with carbon isotopes. Carbon-12 has 6 protons, 6 neutrons, and 6 electrons. That's carbon-12. Atomic number 12, or atomic mass 12 protons and 6 neutrons, 12. Now carbon-13, 6 protons, nice, but 7 neutrons for 13, and 14 is still the 6 protons, that's what gives it the property, but you have 8 neutrons, and these neutrons are the ones that are breaking down and giving off energy and other particles. And basically carbon-14 is decomposing, is breaking down into other atoms. Now, besides carbon, we use a number of other isotopes in biology, phosphorus, potassium, so keep an eye on them. And the idea is that most of these isotopes that we use are going to be radioactive because they are going to give particles and energy that we can trace, that we can follow up, and that's important. So, basic chemistry. You have a couple of atoms here. nucleus, the shells with the electrons, and if you recall, the outer shell is the valence shell where you have the valence electrons. And what is the magic number here? How many electrons do you want to have in the outer shell for the atom to be stable? And the magic number is 8. 2, 4, 6, missing 2. So what does that mean if this guy is missing 2 electrons in the outer shell? This means that this element, whatever it is going to be always looking around to connect with somebody else so it can fill this shell, so it can get 2 electrons from somewhere else to fill out that shell to be stable, to be happy. Now you look at this one, outer shell, only 2 electrons there. So what's easier for this guy? To collect 6 more or to give up those 2? Obviously to give up those 2. So the way the atoms behave in chemical reactions is depending on the valence electrons. And please remember that the magic number is 8. Alright, so there you have it. Now, the reactivity. You are going to have to fill in those shells. So this is what's going to create the bonds, and that is so important in biology. So you can give on an electron, and if you give off an electron, what kind of bonds are you forming there? When electrons are given from one to another, that would be an ionic bond. What happens when you share the electron? So everybody's happy here. When you share, what kind of bond is that? That would be covalent. Very good. So in biology we have a couple of bonds, and you're gonna check your chemistry with this. First we have the hydrogen bonds that are the weakest bonds, but extremely important in biology. And we'll go in detail about the hydrogen bonds in a few minutes. Then we have ionic bonds that are kind of okay. We don't deal with them too much in bio. But then the other one that we deal very much with is the covalent bonds that are the strongest in biology. I know in chemistry you learned that ionic bonds are the strongest, but in chemistry you're talking ionic bonds when you have things that are dry, a chunk of salt, sodium chloride. There is no way you're going to separate the sodium and the chloride together. However, what happens when you put that sodium chloride in water? Which is most biology? Biology is wet. Everything happens in wet solutions. Sodium and chloride separate with very little work. So, please remember, in biology, in wet biology, because we are all dealing in wet solutions, everything is dissolved here, the strongest bonds are the covalent bonds where you share the electrons between molecules or atoms. So, ionic bonding, just to be a quick review. In ionic bonding, one of the atoms that has an extra electron donates the electron, changes charge. The more electronegative attracts that electron, but then because the charges are different, the one accepting the electron becomes negative, the one donating the electron becomes positive, and what happens when you have a positive and a negative? Opposites attract. They get stuck. Basically, I let you borrow my electron because I'm gonna stick with you because I want to keep an eye on my electron. So that's how you have sodium chloride, for example, sodium and chlorine, and a lot of other compounds that are joined by ionic bonds. They work great when they are dry, but the minute you add water to this, what happens to them? They disintegrate. Alright, so please remember that in biology ionic bonds break easily because of water. Now, covalent bonds are the strongest in biology because you have two atoms that are sharing an electron, and this is what's going to form molecules. Hydrogen only has one electron. To be stable, they are looking for another one. So two hydrogens get together and you have hydrogen gas, very stable molecule. Now, In this case, the electrons are shared, and the pull from the nucleus, one proton, is even. So those electrons are perfectly in the middle. They play nice. They share 50-50. Wonderful world. Here you have oxygen with two hydrogens. Oxygen needed two electrons in the valence shell, so grabs one from one hydrogen, one from another, and you have the famous water molecule. What's the problem with oxygen? Oxygen has eight protons in the nucleus. It's an electron sucker. It's attracting things very hard. So what happens with these electrons? Are they 50-50 between the wimpy hydrogen that only has one proton? Are they 50-50 in the middle? Wait, no. They are much closer to the oxygen. Because of the electronegativity, all these electrons are much closer to the oxygen than to the hydrogen. So when you look at the whole molecule, what do you see happening here? That the electrons are mostly focused here, so this section of the molecule, it has a tad negative charge. And what happens to the poor hydrogen? Hydrogen, the electron is not there, is farther out, so now the hydrogen side of the molecule becomes slightly positive. So covalent bonds work great, and here is a non-polar covalent bond because it's 50-50, no polarity. The molecule is totally neutral. What kind of covalent bond do we have here? This is a polar covalent bond.
Katie, this is Monica. Could you come to my desk? Thank you.
This is a polar covalent bond because the molecule now becomes polar. Think of poles, north and south, a magnet, positive and negative. Here you have the negative side of the molecule, the oxygen side, sucking up all those electrons. And here you have the more positive side of the molecule. So water becomes like a little magnet with a plus side and a negative sign on the other side. So this is what makes a polar covalent bond, and this will be a non-polar. Non-polar, basically no charge in the molecule. Polar means that your molecule is gonna be charged. It's gonna be polarized. Please, please, please get this clearly there. You're gonna use it all year long. So, another example of a non-polar covalent, CH4. You pass this gas. This is methane. When we pass gas, one of the gases we pass, a little fart, basically, is methane. Is a carbon molecule. In this case, the black ball here is the carbon, and the four hydrogens around are these orangey things. Now, because carbon is not as electronegative as oxygen, guess what happens here? All the molecules are balanced and stable, and there is no charge to this molecule, totally non-polar, because hydrogen and carbon plays nice. Please remember that. Carbon shares nicely. Obviously went to kindergarten and did all the right things. Oxygen, however, what happened to oxygen? Does not play nice. Is an electron sucker, wants all the toys for himself or herself. So here we have again our polar covalent bond, the example of water. So the hydrogen and the oxygens are attached by covalent bonds, but all the electrons are closer to the oxygen, so the molecule overall has a charge. Now this charge is going to be very important because when you have a molecule that is charged, it's going to interact with other molecules around that are also charged, and that is the secret of water. So let's move on. Negative side, positive side of the molecule, and remember this is known as the Mickey Mouse molecule. Here are the two ears, here is the smiling side of the Mickey Mouse. So, because water is a polar molecule, this is going to allow for the possibility of hydrogen bonds forming between molecules. So, you have here two water molecules, Remember, the hydrogen is slightly positive because it lost the electrons. However, when you have the water together, or any other molecule that might be charged, important, doesn't have to be water all the time. You can have hydrogen bonds with anything. What's going to happen here? The positives and the negatives are going to attract. And that is going to make the molecules kind of join together lightly, and which is very important because that is what makes life on Earth possible. So, we are water-based creatures, and we want to know about water because life occurs in water, inside and out. You are 70% water. I hope some of you have watched the movie or the show or read the books called Dune, D-U-N-E. It's about a world where water is very precious and is recyclable. And the greatest gift that somebody can give to the next generation is once you die, they squeeze you dry. And all your water is passed on to your favorite descendant. And that's the greatest gift that you can give somebody else. Read them, it's pretty good actually. So let's go back to this. So we care about water because everything in our bodies happens in water, and all our chemical reactions that keep us alive are happening in a watery environment. So we know about the polarity of the water molecule because oxygen is electronegative, is an electron sucker. And that is beautiful because what happens is every water molecule is gonna hang on or attach to 3 other water molecules by hydrogen bonds. So it's like you're all holding hands together. Pretend that each one of you is a person or a water molecule, but you hold on hands to another through hydrogen bonds. And that is what makes water stick to each other. You open the faucet and you can see the stream because all the molecules are connected to each other by these hydrogen bonds. This is so good because it's going to allow us to see a number of important properties that we'll talk one by one. So, first thing, and you remember this very clearly from freshman bio, because the water molecules are connected to each other through these hydrogen bonds, they make in the top of the surface of water what is called surface tension. Molecules are together, and if you are something that is not too heavy, like my spoon, and these are my hydrogen bonds, if you are not too heavy, you can sit on top of the water, like that water strider. Now, if you are way too heavy, like my tape thingy, it's gonna fall because those hydrogen bonds are not strong enough to hold that heavy thing. So they are strong, but not that strong. That's why we cannot walk on water. We are way too heavy, too much mass. But these light guys do walk on water because the hydrogen bonds are able to support them. Now, cohesion then is the attachment of one molecule of water to another, polar, they're all charged. Now, the other property of water is adhesion. And that's basically where the water is not necessarily attached to other molecules of water, but to other substances or compounds that are also polar. As long as you are polar, you're going to stick to it. So think of water as a magnet. And where do you attach a magnet? Anything that has a magnetic charge. Same thing with water. So water can attach to the sides of glass. If you spray water on a glass, what happens? Water sticks to the glass and you see these beads because the water is stuck there. If water was not polar, guess what would happen to the water? They would just slide down the glass. But you know that water sticks to things because of the polarity, because it has a charge, and the glass actually is slightly charged too. So that is the property of adhesion. Extremely important. So this is what allows, water to climb up pipettes, any vessel, and you form that meniscus because the water is attaching, grabbing to the sides of the glass, the pipettes. Now remember again that a combination of adhesion and cohesion is in part what allows water to move up the tree through the xylem of plants. So if you have the xylem, skinny tubes, water is moving up, but why? Because water, pretend that this is the xylem, water is attaching to the xylem, making bonds with the xylem, hydrogen bonds, but at the same time, each molecule of water is attached to another molecule of water. So I attach to the xylem, but I also attach to the other molecule of water, and we just keep on basically going up and up and up. Cohesion and adhesion. That helps water move up the trees. Now, water, you know very well, water is a solvent, and it's called the solvent of life because water can dissolve pretty much everything. How does water dissolve pretty much everything? Well, pretty much everything that is slightly polar, that has a charge. So if you have a molecule, a compound like sodium chloride, that is positive sodiums and negative chlorines, guess what happens there? Water is going to sneak around, and the negative side of water, that is the oxygen, is going to be attached to the sodium. And the positive side of the water, that is the hydrogen, is going to be attached and surrounding the chlorine. So basically, the water sneaks in and surrounds these molecules, the positive with the negative, and isolates and separates these compounds. So that possibility of dissolving something, like is shown in this, and all these figures are in your textbook, so just look at them, please. All this works if the molecules are charged, are polar. Got it? Now, what if you have a molecule like this humongous protein that is not charged, no polar? Absolutely nothing. It's not going to be able to dissolve because water has no way of attaching to it because it's totally neutral, totally non-polar. So that's a very important concept that you're not going to need to work on it. Now, let's introduce a couple new words, hydrophilic and hydrophobic. So hydrophilic means hydro, that you like water. If water is polar, what is water going to be attracted to and be able to interact? If water is polar, water is going to be able to interact with other molecules that are polar. So any polar substance is going to be hydrophilic. Salt. Now, what if you have something that is hydrophobic? Is that a polar or a non-polar? Doesn't like water, and if it doesn't like water, means does not have a charge. And I want to introduce you something that you should be familiar with, and this is a nice molecule of fat, typical triglyceride, the stuff that we have everywhere in our body. Now, if you look at this molecule, and I hope you have looked already, and don't freak out because of all the symbols, here are carbons, and every carbon is attached to a hydrogen. And remember, how does carbon play? Carbon plays nice. Carbon shares all the electrons nicely with the hydrogen. So this is a perfectly neutral molecule. If it's a perfectly neutral molecule, what do we call those? We call those, hello, non-polar molecules. Non-polar means no charge. So fats, all fats, butter, oil, you name it, are non-polar. They have no charges. And because they have no charges, water cannot attach to them, cannot do anything. That's why the two of them never mixed. Good? Excellent. So, that's why it dissolves everything, because the molecules of water reorient and can sneak in between these charged molecules. Then, of course, we have the problem of ice. Water is the only molecule that when it's a solid, instead of getting smaller, it gets bigger. It's the most funny thing. Every single molecule, when you freeze it, when you make a solid, because in a solid the atoms are compacted together, they occupy less space. Water is the opposite. Water, you make ice, a solid, and instead of getting smaller, it gets bigger, actually, because the hydrogen bonds are evenly spaced and nicely organized. And when they're nicely organized, the water molecules occupy more space, more volume, even though the mass is the same. And in terms of density, that means that they will have a lower density. And if you have low density, you are less dense, you are gonna float. Think of a glass of water with ice cubes. Where are the ice cubes? On top, because they are less dense than the liquid. Now, why is this so important? Who cares that the ice floats? Well, this is extremely important for all the bodies of water, because when it gets cold, the ice starts forming in the water, but what does every molecule of, or any particle of ice does? Floats. Floats. Floats until you end up having a nice solid layer on the very top. What happens to the water underneath? It's still liquidy. Now, the thicker the layer on the top, remember it's freaking cold outside on the surface, that's what's causing the ice to form. Because this layer of ice keeps on getting thicker and thicker and thicker, because anything that freezes down here goes to the top, what happens at the end? This thick layer of ice works as an insulator. Insulation, just like a cooler, has a layer of insulation that keeps the cold out and the warmer temperature of the water there, warmer. So it prevents lakes and bodies of water from freezing solid. You know that? Think of ice fishing. You have the ice on top and everything underneath is liquidy. And the temperature under the ice remains pretty much constant because it's totally isolated from the frigid temperatures above. Just think of the terrible thing that would happen if it were the opposite. If ice were more dense, it would sink. Just think of what happened to all the creatures that live on the bottom. Think of all the ice, the lakes and oceans freezing from the bottom up. We'll end up with a totally frozen world all over. So please, 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 this is extremely important. And all that because the hydrogen bonds, when they freeze, they get very nicely organized. Now, hydrogen bonds, we are not done. We owe everything that happens to water to hydrogen bonds. So that's a secret, actually. First quarter, most of the questions that have to do with bonds, if you say hydrogen bond, you probably will get it right 50% of the time. So if you are into chance taking in biology, answer hydrogen bond. That's a hint. So, you know water. You have an ice cube, and to melt it, you have to apply heat until finally it melts. Then you have the water, and you want to boil it, and you boil it, until it finally starts boiling. It takes a while. And then, after it finally reaches 100 degrees Celsius, what happens? If you keep on applying heat, water evaporates. Now, these hydrogen bonds that water forms, they absorb humongous amounts of energy. So you have these water molecules all making bonds. You start applying heat. Guess where that energy is going to be stored? Hydrogen bonds. If you stop applying that energy, what happens? that energy from the hydrogen bonds is slowly released. So water takes a long time to heat up, but also a long time to cool off, because all that energy is safely stored in those hydrogen bonds. So water, it works as a beautiful way to moderate climate. Remember, if you live near the ocean, the temperature, yes, we do have winters and summers, but they are a lot milder than if you would live in the middle of the United States, in the middle of Nebraska or the Dakotas, where away from the oceans, the temperatures fluctuate between 110 in the summer and minus 30 in the winter. Same latitude on the coast, we see something different because water absorbs a lot of that heat during the summer, and in the winter, a lot of that heat energy stored in the hydrogen bonds is released, so the temperature does not oscillate as much. You remember this graph? We're almost done, so hang in there. You remember this graph from chemistry? And basically what I want to point here is the beautiful issue of vaporizing. You have your water molecules, right? They are all connected to each other by hydrogen bonds. Guess what happens when you keep on applying energy and those hydrogen bonds get more and more energized and kinetic energy increases and those hydrogen bonds move. What happens eventually because of the high kinetic energy that you have given to those bonds? They break. And when they break, what happens to the individual water molecules? Get to escape. And that's what we call water vapor. Basically, we applied enough energy, enough temperature, enough heat added to the molecules that all the hydrogen bonds are so energized that they cannot hold together with the molecules and they break apart. And then each water molecule is finally free to be released and escape. It's not bonded anymore to all the other water molecules. That's their freedom. You can apply energy and they released. Or you can add something to the water that neutralizes the charges and they also get released. So, what happens when you sweat? When you sweat, your body releases water. Big deal. Water alone is not going to cool you off. What really cools you off is that water molecule is sucking up energy from your body. It's sucking up heat energy. And using that heat energy to break these hydrogen bonds between the water molecules, allowing the water molecules to escape. Every time a water molecule escapes out of your body, it's sucking up, removing from your body a huge amount of heat energy, and that allows your temperature to cool off. That is why when you stand in front of a fan, you feel cooler, because the fan is helping the water molecules break away and remove from your body. Sweating is critical. And what happens with sweating, you release the water. But when the hydrogen bonds break, they break because they are absorbing energy from your body. They are stealing that heat from your body to be free. Basically, you are setting the molecules free. Feel good about it, giving them freedom. And that helps us cool off and bring our body temperature back to normal. So what happens if you do not have sweat glands and you cannot release water? You cannot cool off unless you are constantly applying water from the outside to yourself. And guess what? Water by itself does not cool you off. What that water has to do is evaporate, which is wonderful. Basically, hydrogen bonds break because they are taking energy away from you, and that is what allows you to bring your temperature down. So, Remember, we have sweat glands all over the place. Other animals do not have sweat glands all over the place. Dogs and felines, they don't sweat. What they do is pant. The tongue and the nose thingy are moist. And basically, this is where the water is evaporating. It's not that your dog is extremely tired in the summer. It's just cooling off. The tongue is the cooling device. And that is called panting, releasing water from there. So, to finish up this brings us to the issue of pH. Since we are dealing with water, we are dealing with solutions, and one of the critical components is the pH of your solution. Now, we need to truly understand pH. Most of you talk about pH, oh yeah, 1 to 4, 7 is neutral. What is pH? pH basically is a measurement of the concentration of hydrogen ions. Hydrogen ions in a cell. That's it, or in a solution. Hydrogen ions. Now, how do we measure this concentration? Well, let me give you a little, well, you know that if the concentration of hydrogen is greater than the concentration of hydroxyls, you are gonna, equal. That same concentration here, you have a neutral. If you have a high concentration of hydrogen in respect to hydroxyls, you are acidic, and vice versa, you are basic. You know your scale goes through 1 through 14. What that 1 and 14 and 7 and 10 really mean? pH, that P there, is basically the logarithm of the concentration of hydrogen in a solution. Looky, looky. So, if I have a concentration of hydrogen ions that is 0.003 molar in my solution, stay with me. If I put that in scientific notation, that is 10 to the minus 3. 1, 2, 3, exponential 3. Got it? 1, 2, 3 decimals. Oh, wait a minute. Screwed up here. This should be a 1. There you go. So, 10 to the minus 3. 1, 2, 3, 10 to the minus 3. Got it? So, we have a concentration 10 to the minus 3. Get your calculators out and calculate the logarithm of that. If you get the logarithm of that, guess what you get? You get the number 3. Remember, I screwed up here. This is 1. You get the number 3. So, if the concentration of hydrogen ions is 0.001, which is the same as this, the pH is 3. Now, just quickly, ready? If the concentration of hydrogen is that, 0.0000001, what is the pH of that solution? Let's write that in scientific notation. This will be 10 to the minus 1, 2, 3, 4, 5, 6. 10 to the minus 6. What's the pH of that solution? Come on. pH of this solution is 6. This is what pH means. It's a concentration of the hydrogen ions in a solution. So, here is your concentration. Remember, this 10 to the minus 14 really means that you have 0.012345678 10 11 12 13 14. That's the concentration of hydrogen ions here. And what is the pH of a solution with that? Obviously 14, which is very basic because it has so few hydrogen ions. What's the concentration of hydrogen in a solution that is pH 1? 0.1 molar. Forgot to add the molar there. Which number is bigger? Which one has more hydrogen? This or this? Obviously, that one has more hydrogen. So, more acidic,
And that's what pH is. Please, this is extremely important. You have a table in your math notes. Please complete it so you can work it out. That means that between pH 1 and 2, how many units are really different? It's not 1 to 2, 1 unit. It's 10. Between any of these, the factor is really 10 times. So, ready for the question? If I give you a solution of pH 6, like your urine or your saliva, and then I give you a solution with pH 3, like Coca-Cola. My question is, first, which one has more hydrogen ions? Which one has more hydrogen ions? That one has more hydrogen ions. Question number 2. How many more hydrogen ions does it have? 10, factor 10 to here, and to here another factor 10. What does that make? 1,000 times more hydrogen ions. So, a solution of pH 3 has 1,000 times more hydrogen ions than a solution with pH 6. Good? I hope so. This is fundamental. You will need to understand pH. And remember, what is pH really? Is the concentration of hydrogen ions in a solution. And notice, it's a hydrogen ion, and it has what? A charge. A charge. Now, what's the pH of most living things? Look over here, blood. Inside we are pH 7. What's the concentration of hydrogen ions inside your body? If I go inside, grab your blood and check how many hydrogen ions you have 0. That's a 0. 0, 1, 2, 3, 4, 5, 6, 7 molar. That's how many hydrogen ions you have in your blood right now. Good? One last thing, a parting thought. What is a hydrogen ion? Hydrogen ion is a hydrogen, right? What makes a hydrogen atom? A hydrogen atom is a proton with an electron flying around. This is hydrogen, right? Right. What is a hydrogen ion? Has a positive charge. So what is the hydrogen missing? What the hydrogen is missing the electron. The electron left. When the electron leaves, what do you have left? A proton. Ah, amazing. Please, 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 please. A hydrogen is the same as basically a proton. That's simple. A simple proton. All right, so I think this is all we have to do today. So please make sure that you are on top of this, that you understand the biological application of all the chemistry that you had learned in the past, and that we are ready to go because you will use this the rest of the year. Parting thought or parting concept. Buffers. You've all talked about buffers. You learned buffers in chemistry. Buffers are substances that allow you to maintain the pH at a relatively constant level, whatever that level is. You figure out what concentration you want. Because a buffer, what does it do? To maintain the pH within a narrow range. What do buffers do to maintain the pH within a narrow range? A buffer is a substance with a split personality. If you need to maintain the pH at a given level, the buffer can donate hydrogens. Or, if you are too acidic, what does the buffer can do? It can retrieve the hydrogens from the solution. So I give you and take hydrogens, or hydroxyls as needed, to maintain the pH in the narrow range. Most buffers, at least in biology, are basically weak acids, and we are going to be dealing with them through the year. So please remember, review your buffers. Buffers are substances that can give or take hydrogen ions accordingly to maintain a certain level of acidity in a solution. Good? I hope this helps. Welcome to biology.